Our next topic is going to be on solutions. So we'll go through the general properties, and after that talk about how we make a solution, so solubility and the rates of dissolving solids. We have to spend a lot of time talking about the concentration of solutions, and then we'll get on to some properties, colligative properties, that are very specific for solution. So when we talk about a solution, don't forget, a solution is another term for a homogeneous mixture. And when we talk about homogeneous mixtures, you can have your different components, and of that, you can have solutes and your solvent. And you can have more than one solute. This is the substance being dissolved, and this is not the majority. Okay? The solvent is the dissolving agent, and it's generally the most abundant substance. What's interesting about your solvent is that the solution will typically have the same physical state as your solvent. So in air, since we have 78% of air is nitrogen, air is going to appear as a gas. Now all of these solutes are gases as well. But let's take something like sugar water. This solution appears as a liquid. Like the solvent. Even though we know that our solute, here, the sugar, is a solid. So, soda is a mixture of sugar and water. It has carbon dioxide in it as well. So, which is the solute? So, this is the substance that's dissolved in our solvent. So, the solute will be sugar, and water acts as the solvent. Okay? A solution is prepared by adding 25 milliliters of ethyl alcohol to 75 milliliters of water. So which is the solvent? And we have to take a look and say, okay, so we want the majority component. And if you look, that would be the water. I have more water in there than I have ethyl alcohol. All right, so here's some common types of solutions, and you can see it doesn't always have to be a liquid. Air was our example for gas. Okay, sodas were our examples for liquids, and alloys, typically like brass and certain types of alloys, those are solids. Okay, and so basically you also have examples of solid solutions. Typically we call these alloys. Down here, a solid with a solid, that's an alloy. Okay, what about these solutions? How do I know it's a homogeneous solution? And we talked about that before, where the solutes were uniformly distributed. Okay, now remember, when we talk about solutions, it's a homogeneous mixture, so we have variable concentrations of components. Okay, the other thing is that when you dissolve your solute, it looks like it disappears, but it really hasn't. What happens is now you have the individual molecules or the ions floating around in a large amount of solvent. And that's why you can't see it anymore. We don't have our Superman eyes. Okay, so when you dissolve your solute, it's on the molecular or ionic size. Okay, it's usually transparent. You can look through it. It can be colored or colorless. So soda water, like tonic water, is colorless. If you look at something like Coke, Diet Coke, those are colored. but they're transparent. You can look through them. Okay. The other thing is that if you let it sit, you don't see the solute settle out. So it always remains dissolved in solution. And finally, we can separate it by physical means. Remember, this is part of how we know it's a mixture. You don't need to do chemical means. Remember, chemical means a chemical reaction, then we're looking at a compound. We're not looking at a mixture. When we look at mixtures, we're going to be using physical means. So evaporation, filtration, things like that. So those are the properties of a true solution. How do we know how much will our solute go into our solvent? And one of the ways we can describe it is called solubility. It's the amount of substance that will dissolve in a specific amount of solvent at a given temperature. So, one, we know that solubility will change as our temperature changes and is going to depend on what the solvent we use. Okay, and we have to standardize it. So typically we do 100 grams or 100 milliliters of water. Okay, and you'll see your temperature listed there as we look. This is the maximum amount though. So this is mass solubility, because notice I'm giving everything in grams. And when we do this, this is the maximum amount of solute that can go in water at that temperature, or the solvent at that temperature. Okay, so in our example, if I had put in 29 grams of potassium bromide in 100 grams of water, only 27 will dissolve and 2 grams will be on the bottom. If I put in 24, then basically all of that will dissolve. Okay? What about terms like miscible and immiscible? These apply to two liquids. So miscible is when two liquids dissolve in each other. This would be like water and ethyl alcohol. And immiscible, again, they do not dissolve in each other, and this is like oil and water. Okay, but those two terms apply to whether or not we're looking at two liquids. Okay, so what are these solubility rules? All right, make sure you have them available to you, and you have a more extensive one in the double displacement experiment that we do. Always soluble, no exceptions, if your cation is sodium, potassium, or ammonium, and your anion are nitrates or acetates. So if I said, oh, listen, if I gave you sodium phosphate, is that soluble? You would write AQ. Or is it insoluble? You'd write S. And you say, oh, listen, my cation's is sodium, so of course it's going to be soluble. Okay. What happens if I gave you something like, let's like chromium acetate, 3-acetate, chromium 3-acetate. There we go. Is that soluble or insoluble? You say, oh, look it, it's an acetate. So because I have an acetate, it's going to be soluble. All right, now let's take a look at the more interesting ones. We'll have exceptions here. So the halides, chloride, bromide, and iodide, they're general. So the first thing you're going to say is, oh, they're soluble. And then you're going to look and say, is it silver ion, mercury 1 ion, or lead 2? So if I gave you, and remember, it's mercury 1, not mercury 2. So if I gave you something like sodium chloride, you say, is it soluble or insoluble? Oh, it's soluble. Okay, it's not silver, mercury 1, or lead 2. If I gave you something like mercury 1 bromide, you say, oh, bromides are soluble. Oh, wait a second, I have mercury 1. It's insoluble, so you put a solid. All right. If I say, oh, what about silver iodide? You say, oh, iodide, soluble. Oh, up. It's one of the exceptions. Solid. Okay, so that's how you use this table. Let's take a look at sulfates. Sulfates are generally soluble. Okay, these are slightly soluble, so some will dissolve, but not a lot. But generally, sulfates are soluble. But the ones that are really insoluble are barium, strontium ions, and lead-2 ions. So again, the way you would do it is that if I gave you something like ammonium sulfate, oh, that's a double whammy here. Why? Because ammonium, always soluble, no exceptions. So we already know this is going to be aqueous. But what happens if I gave you iron 2 sulfate? Well, sulfates are soluble. It's not any of these cations, so it's going to be aqueous. What happens if I gave you lead 2 sulfate? You take a look, say, oh, look, they're soluble. Oh, wait a second. Lead 2 is an exception. It's going to be a solid. All right, let's go to the next group. Now this group, we're going to start on the right because these are mostly insoluble. So if I gave you something like calcium sulfide, then the first instant you're going to say, oh, it's going to be a solid because it's insoluble. And then you take a look here and say, oh, my cation is not ammonium and it's not the group 1 cation, so it's going to be a solid. What happens if I gave you potassium sulfide? You say, oh, it's going to be a solid. Wait a second, that's a group 1 metal cation. Therefore, it's soluble. And this is also, if you look, there's consistency between these two. What happens if I gave you iron 3 phosphate? Well, that is going to be insoluble because it's this, my cation is not ammonium and it's not a group 1 metal cation. What happens if I gave you something like ammonium carbonate? Well, we know ammonium ion is always going to be soluble, so that you put in water will make an aqueous solution. So these guys, the carbonates, phosphates, hydroxides, and sulfides, are generally insoluble. So the first go-to is, I think it's a solid, and then check to see if you have your cation is one of the exceptions. Okay, so barium sulfate. So remember, sulfates tend to be soluble except barium, strontium, and lead 2. And because of that, because we have barium as my cation, we're going to have to say that it's insoluble because that's an exception right here. All right, what about sodium chloride? Well, anything that has a cation of a sodium ion is always soluble. So it's soluble. All right, silver nitrate. Well, with the nitrates, it's always soluble, no exceptions, like the acetate. So because of that, we don't need to go any further. Silver hydroxide. Hydroxides tend to be insoluble. This is not ammonium, and this is not a group 1A metal cation. So it's going to be insoluble. Okay, ammonium carbonate. I think we already did something like this, but with ammonium, it's always soluble. Okay, now what about factors that affect solubility? All right, so how do we know? Can we predict whether something's going to be soluble or not? And we follow this rule: like dissolves like. So polar compounds dissolve in polar solvents. So here we know that water is polar. Okay, and with the ethanol, actually that's methanol here. Okay, we have something like this. So again, we have a polar molecule. Delta plus, delta minus, delta plus, delta minus. They're both polar. They both can hydrogen bond. They both have dipole-dipole interactions, and they can always have their London dispersion forces. So polar compounds will dissolve in polar solvents. So these two are going to be miscible. Okay, nonpolar compounds dissolve in nonpolar solvents. So carbon tetrachloride, okay, remember this is a nonpolar. The bonds are polar because this is symmetrical. It's a nonpolar molecule. Now look at this. This only has carbons and hydrogens, so your carbon-carbon bond is nonpolar. The difference in electronegativity for a carbon-hydrogen bond is 0.4, so it's still considered nonpolar. So this is a nonpolar molecule, so these two will dissolve in each other. Okay, so let's take a look at ionic compounds. So when we look at ionic compounds, how does that work? It happens that my cation, let's take a look at sodium chloride. If I have my cation, which is a sodium ion, the waters will surround it. So now I have around my positive sodium ion all these partial negative charges from my water. I have lone pairs and I have the dipole. What about chloride? Well, chloride has the opposite. All of my delta positive hydrogens are going to be close to the chloride. So now I have a charge attraction, a negative charge on my chloride to the partial positive on my hydrogens. So if my attraction between my ions is low, then my sodium ion may prefer to be surrounded by a bunch of oxygen atoms which love it as well. So that's how these dissolve. What happens if I have a very strong interaction? So remember Coulomb's law. Let me put this down here. Coulomb's law, the force of attraction is equal to K times Q1, Q2 over R squared. And if you look at Q1 and Q2 relatively, this is +1 -1. This is +2 -3. So this has a 6-fold stronger attraction than sodium chloride. So it tends to be something like this because my force of attraction is so strong. Tends to be, it's not guaranteed, you'll tend to find more of these high charge compounds, ionic compounds, where the ions have high charges. They tend to be more insoluble. And if you look at the solubility rules, it's not 100%, but it's a rule of thumb that you can use just to get a feeling for it. If I have two really strong magnets, it's hard to pull them apart. So it means that the water is too weak to pull them apart. If they're weak magnets, then it's easier to pull them apart, and that's what water can do. So if you look, which ones tend to be insoluble? Phosphate, that's a -3 charge. Carbonate, that's a -2 charge. So you have the higher charged ions tend to be less soluble. Like I say, it's a rule of thumb. It's not going to be 100% or even 90% as some of the other types of patterns we see, but it is definitely a pattern. Okay, what about solubility? For the most part, when we're looking at solids, the solubility will increase with temperature, although there are exceptions. Okay, so our red lines, it increases with temperature, but something like my lithium sulfate, that has a slight decrease. You can see this is going down. Everything else here for my solids is going to be increasing. Now, what about gases? Gases always decrease in solubility when the temperature goes up. So, with increasing, solubility decreases with increasing temperature. Okay, and why is that? So if I look at, suppose here are my liquids, and I have a gas here. Well, the reason the gas is dissolved in the liquid is because it's trapped in there. And as I increase the temperature, because all my liquids are now moving back and forth a lot more and moving a lot more, it's easier for the gas to not be trapped and to escape. And that's why the solubility decreases. Now, if you ever tried this, and I'm not sure that I recommend it, but what I would do is on a hot day, if you have a hot carbonated drink, when you open it, you tend to be a lot more careful because it tends to spray a lot more than if it had been in the refrigerator for 24 hours and it's nice and cold. And when you open it, it tends less to bubble over. So next time you have a carbonated drink, take a look and you'll see the difference because of the difference in temperatures. And that's because carbon dioxide is a gas, so it's less soluble at higher temperatures. Okay, so we talked about why it's easier. Okay, what about pressure? Now, we've gone through pressure with gases, and we haven't really talked too much about liquids or solids. So when we talk about solubility and pressure, we're really talking about the gas solubility. We really don't affect liquids and solids too much in terms of the solubility. Now, when we do that, basically, as I increase the pressure, I'm going to increase the solubility. Now, why is that? Let me just draw a quick picture here. Okay, so I may have more text, but let me draw the picture and explain it in my little caveman drawing way. I want Erlenmeyer here. I just want a regular container. So suppose here's my regular container, and I have a little piston here that I can push down. Here, these are my liquids, okay? And here are my gases. When I push down now and increase the pressure, so I push down, and so now my pressure has increased. There's not a lot of space, so what I've done is I'm actually pushing some of those gas molecules in solution. I'm just physically forcing it in. Okay? And if you notice, when you buy something like, let's say, a carbonated soda, when you look, it's clear, it's a transparent, it's a homogeneous solution. It's under pressure. You can't really squeeze the bottle too much, the plastic bottle. If I unscrew it so, and you hear it fizz because all that high pressure now escapes, so it tries to equilibrate with the outside atmospheric pressure, then one, all the gas bubbles that were dissolved in there now can actually escape the liquid. And so that's why you see bubbles forming on the side of your plastic bottle container. Okay, so You've decreased, because you decrease the pressure, you decrease the solubility, and that's how all the gas comes out. All right, saturated and unsaturated solutions. So saturated solution, it contains the maximum amount. Now remember how we talked about solubility? So the 27 grams of potassium bromide and 100 grams of water at 23 degrees Celsius, that was the example. That if you have 27 grams dissolved in that water to give you that solution, that is a saturated solution. An unsaturated solution, what does this mean? I can actually add more solute. Okay, so what happens is if I have a solution in here and I'm adding more solute. In a saturated solution, you'll just see the solute sink to the bottom, and no matter how much you stir it, the amount that you add is the amount that you see on the bottom. That tells you you have a saturated solution. That solution can no longer hold any more solute. Okay, what happens if instead I add more solute and it just dissolves? That means that this original solution was unsaturated. It could still hold more solute. It didn't reach the maximum amount yet. Okay, supersaturated solutions. How do you get a supersaturated solution? It contains more solute than a saturated solution. How is that possible? So remember, solids tend to have a higher solubility at higher temperatures. So if I heat my solution, that means that I can actually dissolve more solute. Now once you do that, then you allow to cool. And when you let it cool, if there's no way for my solute to come out, then this is supersaturated. It is an unstable condition, and what happens when you have a supersaturated solution, if a speck of dust, if you drop a crystal in there. So let's go ahead and drop a crystal. What will happen to the solution is this. Here I'm dropping one crystal. And if it's supersaturated, then what will happen is I get a lot more solid than what I added. That meant that this was supersaturated. And oftentimes this is accompanied by an increase in temperature. Okay, so it's holding in that solute, and now that it can let go and go into its more energetically stable state, it's got to release all the energy. So oftentimes you'll see that when I go have a supersaturated solution, add in a crystal, I get a lot more solid than when I started with, and the temperature of the solution increases, and then it begins to cool down again. Okay. All right. So if I have a solution, okay, and I add 9 grams of potassium chloride to 20 grams of water at 20 degrees, will it be saturated or unsaturated? So this is per 100 grams of water. So if I say 9 grams of potassium chloride and 20 grams of water, so we want to find out what the solubility is per 100 grams of water. And what we get is 45, right? Okay, so this is the equivalent to saying I want to put 45 grams of potassium chloride in 100 grams of water. Okay, now we look at the graph and we say, oh, here is 20 degrees. Okay, and we know that's what we're looking at. So at 20 degrees, and let's find my graph. This graph right here is potassium chloride. So I'll go up, go all the way to potassium chloride, and look at where's the amount? About 35 grams. So when I add the 45 grams and it dissolves, that means only 35 grams will dissolve, and 10 will just stay at the bottom of the jar and will not dissolve. Okay, so because I'm above this line, then this is where I max out. It's going to be saturated. I will not be able to dissolve all of that potassium chloride in my solution. Okay, so when we look at effective particle size, then basically what we're saying on the first one is that it's only at the surface of my particle when it's interacting with, let's say, my solvent is water. It's only that the surface and this interaction is allowed will my solid dissolve. So anything in the interior here, because it doesn't see my solvent, it won't dissolve. It's still just part of the crystal. It doesn't realize it. If you take a large box, okay, and you have your surface area, okay, so let's just say it's 1 meter by 1 meter by 1 meter, okay. If I do that, then basically I have 6 sides, so I have 6 square meters of surface area. Okay, now let's take that same cube, and all I'm going to do is I'm going to divide it in this direction into 10 pieces, this direction 10 pieces, okay, and then now that direction 10 pieces. So now what I have is I have basically 1 centimeter cube. And how many do I have? Let's see, 1 meter cubed is equal to 100,000. 2. No, more than that. Okay. Because I have the interior ones too. So now I have, if I look at 1 cubic meter, it should be 1,000,000 cubic centimeters. If I look at 1 cubic centimeter, then the surface area is 6 square centimeters. Okay? But now I have, this seems pretty big, this is really tiny. But don't forget, how many do I have? I have 6 times, I have how many cubes here? I should have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I have 1,000,000 of those little cubes. So now my surface area is going to be 6,000,000 square centimeters. Okay. If we just take a look and convert this so we can compare meter squared to centimeter squared to centimeter squared. So this is going to be 6 times 10,000, 2, 3, 4 centimeters squared. Okay, so now you can see the difference. If I just take that same volume and I chop it up into little itty bits, then I have a much larger, in this case it's going to be 100 times more surface area, and so it'll dissolve faster. And you can do this with your coffee or your tea if you put sugar in your tea. If you buy those lumps of sugar, take 2 lumps and compare it with just getting the same value, which is what, 2 teaspoons of small granulated sugar, and dissolve them both in the same hot tea or hot coffee, and just let it sit there. And your small particle size will dissolve faster. Okay, what about temperature? So compared to hot tea and cold tea, of course, if I increase the temperature, the rate of dissolving my solid will increase. That's not a big surprise because basically if I'm trying to dissolve it and get it to distribute, having a higher kinetic energy and my solvent molecules moving around is going to help that. Okay, it strikes your solids more rapidly and basically it will distribute the solute molecules more easily across your whole solution. Okay, what about solute concentration? Okay, so the rate is highest at higher concentration, decreases at lower concentration. Okay, so we can see that over time, basically as I give it time, as I approach saturation, it'll just take longer and longer to dissolve. Okay, all right. What about agitation stirring? Well, you are putting in mechanical work. You're adding mechanical work. Part of it is making those particles smaller. Okay, that increases the surface area. All right, so again, we did this earlier. If we take a look at the surface area, all right, and here they're using the 1 centimeter, but basically you have 1,000 cubes at 60 square centimeters or 6.06 square centimeters. So basically that increases the size. So here we can see that with the small crystal, it's not a lot, but we have a lot of cubes in here. So we have more surface area than if we just had one 1 centimeter square crystal. Okay, a reaction medium. So the purpose of dissolving reactions, okay, when we have a reaction, since our solute is going to be in a solution, solute is already on the molecular level. And is easier for my reactants, okay, to come into close contact when both are in solvents. Okay, so here they're just giving an example. If I put potassium chloride here, and then I put next to it a solid cube of silver nitrate, nothing's going to happen. However, if I dissolve them in water, then what do I have? So in my solution, I don't have a solid potassium chloride crystal. I have potassium ions and I have chloride ions. Here, I don't have silver nitrate crystals. I have silver ions and I have nitrate ions. So when I mix the two, my potassium ion can either come into contact with the chloride ion or the nitrate ion. My silver ion can come into contact with the nitrate ion, but as soon as it comes into contact with my chloride, it forms a solid. So what you'll see is that my solution gets very cloudy, and give it time, and your solid silver chloride drifts to the bottom. Okay, the potassium nitrate, since we know it's still soluble, stays in solution as its component ions. All right, so we'll talk a little bit more about how to write those equations down. But let's talk about how we quantitate our solutions. Okay, so let's talk a little bit about how we can describe solutions. And one way is we can talk about it with qualitative expressions, such as this is a dilute solution, or this is a concentrated solution. Dilute solution has a small amount of solute dissolved in there. A concentrated solution has a relatively large amount of solute in there. The problem with these qualitative expressions, although we use them a lot, like this orange juice tastes very dilute, or it's concentrated orange juice, is that what might be dilute to one person, there's a range of values. So if I say make a dilute solution, two people could make dilute solutions, but they're still different. So what we need is we need a quantitative way of describing our concentrations. So the ones we're going to focus on will be mass percent. So the mass of the solute divided by the mass of solution times 100%. And the mass of solution here is, when we only have one solute, is going to be equal to the mass of solvent plus the mass of the solute. Okay? Parts per million is basically that same expression, but times a million. Mass per volume, you'll sometimes see, and volume per volume. The only time I know of a real-life example is when we're looking at the liquor section, where you're looking at 20 proof, 200 proof is the same as 100% volume to volume. So 40 proof, we're talking about alcohol. So this is typically a liquid solute. Liquid solvent is 20% volume of alcohol per volume of solution. Okay, we will spend a lot of time with molarity, because you can see it's moles of solute divided by liters of solution. And with this, we can use this concentration in particular, talking about reactions. So let's focus on these two, but just be aware of the other ones. And we'll mention molality a little later. That's moles of solute, but instead of liters of solution, it's kilograms of solvent, not solution. So calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of sodium chloride in 150 grams of water. So first, before we do anything else, mass percent of solution is going to be, the equation is the mass of the solute divided by the mass of solution times 100%. And mass of solution, remember I mentioned, with only one solute, it's going to be equal to the mass of the solvent plus the mass of the solute. Okay, so the mass percent of sodium chloride in solution is equal to 50 grams of sodium chloride divided by the sum. So 150 grams, this is from the water, plus the 50 grams, that's from my sodium chloride. This is all times 100%. Okay? And what we get is 25%, and this is 3 significant figures. So, and the bottom will be in the end 4, so it will be 3 significant figures. So 25.0% by mass. Okay? What about the mass of sodium carbonate needed to make 350 grams of the 12.3% aqueous solution? Okay, so what's the definition of this? Well, that means that 12.3 grams of sodium carbonate is in 100 grams of solution. And that's my 12.3%. But that's the same as saying, oh, some X grams of sodium carbonate, but we want 350 grams of solution. All right, so now let's solve for X. So X is going to be equal to 350 grams of solution divided by 100 grams of solution times 12.3 grams of sodium carbonate. And that's going to be in 3 significant figures. That's 43.05 grams of sodium carbonate. You need to round it. That gives us 43.1 grams of sodium carbonate. Okay. Molarity. So let's go on to the next concentration unit. And we've done percent enough that it should be, remember it's part divided by whole times 100%, and you just need to know what is my part and what is my whole. Molarity, you should know this definition inside and out, kind of like, you know, the density equation inside and out. And we use this in multiple ways. You can look for molarity or concentration. The abbreviation for molarity is a capital M. If I want the moles of solute, then I multiply both sides by the volume. So it's my concentration in molarity times the volume. This is in molarity, and the volume is going to be in liters. And now I'll get moles of solute. What happens if I want volume? So if I want the volume in liters, then it's going to be equal to the moles of solute divided by the concentration M, and that's going to be in molarity. So you're looking at, from this one equation, you can derive this equation to get moles of solute and this equation to get volume. When we make the solution, always add your solid solute first, so that when you're done adding your solvent, it goes to the very line here and you know the exact volume, because we're looking at the volume of solution, not the volume of solvent added. Okay, so let's do a molarity practice. So what is the molarity of a solution prepared by dissolving 9.35 grams of potassium chloride in enough water to prepare a 250 milliliter solution? So molarity is equal to moles of solute divided by the liters of solution. Now we have the milliliters of solution, so what we're going to have to do here, before we can use this equation, we have to, 1, get the moles of potassium chloride, and 2, convert milliliters to liters. Okay, so to get the moles of potassium chloride, we're going from mass and we want moles. So what do we need to do this conversion? Molar mass. So potassium should be 39.0 39.10, and chloride or chlorine is 35.45. So our molar mass is equal to 39.10 plus 35.45. I get 74.55 grams per mole. So let's finish getting our moles here. So 9.35 grams of potassium chloride, 74.55 grams of potassium chloride is on the bottom for every 1 mole potassium chloride. And what we get, 0.35, we invert it, is equal to 0.1254 moles of potassium chloride. Now we know it's 3 significant figures, but I'm not rounding it yet until we finish the whole problem. So just make sure you keep track of, if I'm multiplying this, I was stopped at 3 significant figures. Now that we've done that, before we can use our equation, we also need to convert milliliters to liters. So we know that the volume is 250.0 milliliters. I know that for every 1 milliliter, it's the same as 10 to the minus 3 liters. So that's going to be equal to 0.2500. These zeros are significant, so don't drop them. Liters. Okay, so now I have liters, I have the moles. Now we can move on to our equation. And I'll put that in dark green, or in green. So molarity is going to be equal to 0.12542 moles of solute, moles of potassium chloride, divided by the volume, which is 0.2500 liters of solution. Remember, those zeros are significant, so you can't drop them. And once we do that, remember, this is 3 sig figs, that's 4. So our answer will be in 3 significant figures. We get a 0.50168 molar potassium chloride solution. 3 significant figures, this is higher, so we're going to round up. 0.502 molar potassium chloride solution. Okay, so you're just going to look at your formula, which you should know, and then basically make sure you get all the values and in the appropriate unit. So how many grams of potassium hydroxide are required to prepare 600 milliliters of a 0.450 molar potassium hydroxide solution? Well, we can't, from our equation, molarity is equal to moles of solute divided by liters of solution. Okay, now why did I pick that? It's not just because we're in that chapter, but look at, you're given the concentration, so we know we're going to have to use that somewhere. We don't have in here grams of KOH, but I do know how to go from moles to mass. So really, this is going to be 2 steps. Okay, here to go to moles to mass, I need the molar mass of KOH. So the molar mass of potassium hydroxide is 39.10 plus 16 plus 1.008 . Okay, so we're going to get something like 56.008 grams per mole. I'm going to round it because this is where your precision is, 56.01 grams per mole. So we're going to need that. Okay, let's rearrange our equation 1 first. So for 1, we're looking for moles of solute. So moles of solute KOH is going to be equal to the concentration times the volume, and that's got to be in liters. Okay, we have 600 milliliters, so we need to do conversion. So the volume, why I put my decimal point there, is 600 milliliters, and we know to 1,000 milliliters in 1 liter. Okay, so what we get is 0.6000 liters. Okay, now that we have the correct units for our volume, we're given actually molarity already, we can get the moles of potassium hydroxide. So that's going to be equal to 0.450 molar, which is in moles per liter. So that capital M, you can just replace it with moles per liter. And my volume, we said, was 0.6123 liters. This is 4 significant figures. This is 3. So our answer, we'll underline it so we know it's 3 significant figures. So 0.450 times 0.6000, and I get something like 0.270 moles of KOH. Okay, so we finished number 1. Now we need to convert from moles to mass, and that's why I needed molar mass. So let's do the calculations now to get the mass of KOH. So we have 0.270 moles of KOH, and I know it's 56.01. Wait, 0.08, so hold on, I'm going to do that. 0.01 grams for every 1 mole of KOH. And so what we end up with is the following. We get 0.270 times 56.01. I got something like 15.1 grams KOH. Oh, right here. Okay, so that's how you did. We started off with writing down the formula and making sure we had everything we need. In this case, we saw with the formula I had moles, but now you've practiced enough. As soon as you see moles and you know you need mass of the same substance, you can kind of know what that step's going to be. So once we do that, we can start filling in and completing this question. Okay, so now that we know how to calculate molarity and get moles of solute and volume of solutions, we also can use our concentration as a conversion factor when doing stoichiometry problems. So for instance, how many milliliters of 0.175 molar mercury 2 nitrate are needed to precipitate 2.50 grams of potassium iodide? So let's look at the balanced equation. And what we're trying to do is find out how many milliliters of our mercury 2 nitrate we need. So we're starting off with the mass of potassium iodide. But in order to relate these two different substances, we need our mole to mole. So from the mass of potassium iodide, we need to get moles of potassium iodide. And from moles of potassium iodide, we need to get the moles of our mercury 2 nitrate. Now we can do this all in one conversion, but I usually like to do 2 steps. So once I have the moles of mercury 2 nitrate, then the second is if I look at my molarity equation, we want our volume, okay? So we're going to rearrange this equation. We want the volume. This from the equation here, it's going to be in liters, and that's going to be equal to moles divided by molarity. So the moles of mercury 2 nitrate divided by the concentration in molarity, which we're given, okay, for the mercury 2 nitrate. Once we've done that, now all we need to do is do a conversion. We need to convert, because that's in liters to milliliters. Okay, so let's take a look and see what information we need. And I'll put it up in the upper right. We need the molar mass, the potassium iodide for this part, the mole-to-mole ratio between potassium iodide and mercury 2 nitrate. So that's step 1. Step 2, we want the moles of mercury 2 nitrate, but we get that from step 1 right here. And we need the concentration, which is right here. So we're okay there. And then the conversion, and we know the conversion factor between liters and milliliters. So let's start with step 1 first. Because I need the molar mass of potassium iodide, so let's take a look. Potassium, I believe, is 39.10, but let's double check. Okay. So potassium iodide is a 39.10 plus the iodine is 126.90. And what we get is the molar mass of 6.10, or 39, excuse me, 0.10 plus 126.90. We get something like 166.00 grams per mole. Okay, so we have this. This is 2 moles. Is the potassium iodide is equivalent to 1 mole of my mercury 2 nitrate. So let's go ahead and do this calculation first. So we're given 2.50 grams of potassium iodide, and we determined the molar mass to be 166.00 grams, potassium iodide for every 1 mole of potassium iodide. And we know for every 2 moles, by mole-to-mole ratio, every 2 moles of potassium iodide requires 1 mole of mercury 2 nitrate. So what we get in terms of the moles of mercury 2 nitrate is 2.5 divided by 166 divided by 2. I get something like 0.0075301 moles. Okay, and this is 3 significant figures, so 1, 2, 3 significant figures. Okay, so we finished step 1. We obtained our moles of mercury 2 nitrate. Step 2 was to use our equation to get the volume. So to get the volume, we did this. The volume in liters is equal to moles of solute divided by the concentration and molarity of the solution. So the moles of solute we know 0.0075301 moles divided by the concentration, which is given right here, 0.175 moles per liter. That's the same as the capital M. So when I do that, by 3 divided by 0.175. I get this for my value. Zero point 0.043029. Remember 3, 1, 1, 2, 3 significant figures, liters. The last step was to convert liters to milliliters. So we know 0.043029 liters. We know that 1 liter is 1,000 milliliters. And we know it's going to be 3 significant figures. This is a 2, so we're going to leave it as is and not round. So when we move our decimal placement, it's 43.0 milliliters. It's 3 significant figures, and that's our volume in milliliters. Okay? Now bear in mind, when we do stoichiometry, before with chapter 9, we started with just masses, or we can do the number of atoms or molecules. Okay? So our solution map before, we had moles of A to moles of B, and then we went to mass of B. And we could have mass of A. And so we were using all our molar masses and our mole to mole ratio. Now we could use the volume of A if it's in a solution, as long as we know the concentration in molarity, because we know that equation, we can get the moles of A. Likewise, if I know the concentration in molarity for B, then I can get the volume of B. So the key, remember, is our mole to mole ratio. And now we have multiple ways to get the moles of either A, and from the moles of B to get the various values back. So what we followed was we were given the mass. You started off with the mass of potassium iodide. We ended up getting the moles of potassium iodide, and then we ended up getting the moles of mercury 2 nitrate. And from the mercury 2 nitrate, because I was given the concentration, I could finally get the volume. So we followed the path in yellow. So now you have a lot of different permutations that you could be following in order to solve these types of reactions and stoichiometry problems. Okay, so let's do this one. Here you have your balanced equation. How many grams of silver chloride will form by adding enough silver nitrate to react fully with 1,500 milliliters of 0.4 barium chloride solution? Okay, so what are we given? So what about the silver nitrate? So we already know we just added enough so that this is completely used up. Okay, so we'll just focus on the amount of barium chloride. So what we're given is the barium chloride, the volume of barium chloride, but we want the mass of silver chloride. So we're going to have to change our substance. So we need to get our mole to mole ratio. So from the volume, I can get the moles of barium chloride because I am given my concentration in molarity. From the moles of barium chloride, I can get the moles of silver chloride with our mole to mole ratio based on my balanced equation. And from the moles of silver chloride, they want mass. I can get the mass of silver chloride as long as I know the molar mass. So, first part, that first step here, we're going to use the moles of solute is equal to concentration times volume in liters. Okay, is my volume in liters? No, so I'm going to have to convert. Let me just change my color, so I'm going to write it up here. 1, convert volume, convert milliliters to liters to, I'm going to use my equation to get moles. Okay, and that will take care of this step right there. Then I need my mole to mole and then my molar mass. So then I need mole to mole ratio given here and the molar mass. So now the molar mass of silver chloride, and then I'll erase it after I write down my third step so we can have some space here. Silver is 107.87. And my chloride is 35.45. So for silver chloride, is 143.32 grams per mole. So let's put this all together. Okay, let me store my molar mass up here, 143.32 grams per mole. That's my molar mass of silver chloride. Okay, and what am I putting together? Let's put together our various steps. So, step 1, convert milliliters to liters. Step 2, use the equation to get moles. And this is going to be moles of barium chloride. Step 3, go from moles of barium chloride. Use our mole to mole ratio to go to moles of silver chloride, and then use our molar mass to go get the mass of silver chloride. All right, let's do step 1 first. So step 1, convert milliliters to liters. 1,500 milliliters. We know it's 1,000 milliliters in 1 liter. So the volume of my solution will be 1.500 liters. That's step 1, the volume of my solution. Step 2, I'm going to use my equation to get the moles of barium chloride. So step 2, I'm going to put down here. Okay, so for step 2, my equation was moles. I took my molarity equation, multiplied both sides by volume, is equal to concentration times volume, and this is in liters. Concentration was 0.400, and remember, the capital M can be substituted for moles per liter. This is for barium chloride. And my volume, we said, was 1.500 liters. Okay, so the moles of barium chloride is 0.4 times 1.5. I get 0.600 moles of barium chloride. Okay, so we finished step 1, we finished step 2. So now let's do step 3. So step 3 will look like this. I finished just calculating. I had 0.600 moles of barium chloride. I need my mole to mole ratio, and I know that 1 mole of barium chloride will give me 2 moles of silver chloride. And I need to get my molar mass. I know for every 1 mole of silver chloride, it weighs 143.32 grams. Okay, I'm going to put my work up here. So 0.6 times 2 times 143.32, and I get something like 171.984 grams of silver chloride. This is 3 significant figures, so I'm going to stop here. I have to go up 172 grams of silver chloride. Right there. And it so happens it's A. So all this work, those 3 steps we just did. 1, converting from milliliters to liter. 2, using our molarity equation to get the moles of solute. 3, now we finish our solution map, and then we get 172 grams of silver chloride. All right. Dilution. So suppose you have a concentrated solution, but you actually don't want it concentrated, you want it dilute. Or you have a dilute solution, you want to make more, and so you need to know how much concentrated solution you need. So the basis behind it, and everyone loves this equation, it's M1 V1 is equal to M2 V2. And how does it work? So the way it works is this. Here is my concentrated solution. It has a concentration of M1. It has a volume of V1. So the moles is equal to M1 V1. Now suppose I just add solvent. So when I'm diluting something, I'm just adding solvent. Those are my solutes. Okay? When I add solvent, now I have a different volume. Okay? It's V2. That's my new volume. I have a new concentration, M2. But it turns out, because I'm only adding solvent, the number of moles of solute have to stay the same. Okay? So because of that, we know that the moles here, after I added solvent, is equal to M2 V2, and I know these two are equal. So that's how we get M1 V1 is equal to M2 V2. Now, these subscripts don't tell you much, but generally, I use the 2's for the dilute solution, and I use the 1's for the concentrated solution, so you can keep track of everything. Okay? So, what volume of 12 molar hydrochloric acid is needed to make 500 milliliters of a 0.1 molar hydrochloric acid? So notice my substances stayed the same, so I do not need any mole to mole ratio. I'm just changing the concentration of my hydrochloric acid solution. So since we know it's a dilution, we're going to go right down in my equation, M1 V1 is equal to M2 V2. Now let's go ahead and record what everything is. I'm looking for the volume of the concentrated solution. So I'm looking for V1. Okay, M1 is going to be equal to 12 molar. The dilute solution here, I know that V2 is equal to 500 milliliters, and M2, excuse me, is given at 0.10 molar. So when we do this, I can solve for V1. It's very similar to doing your gas laws, actually. So M2, now we can plug everything in. M2 is 0.10 molar. V2 was 500 milliliters. And M1 was 12 molar. And notice I didn't do anything with my units because as long as the units for concentration are the same, as long as the units for volume are the same, you're set because my units canceled out. So V1 is equal to 0.1 times 500 divided by 12. Okay, so we get, this is 2 sig figs, 4.2 milliliters. And this is my 12 molar hydrochloric acid solution. Okay, so now let's do one more practice. All right, so let's try this. Calculate the molarity of a sodium hydroxide solution prepared by mixing 100 milliliters of 0.2 molar sodium hydroxide with 150 milliliters of water. So here, I started off with 100 milliliters. And then I added 150 milliliters. So in my final solution, what is my volume? Well, if I started off with 100 and I added 150, so the volume is going to be the sum of the two. So this volume, so V2, is actually 250 milliliters of solution because I added the two. Okay, so now that we have our V2, we know this is V1. Okay, we know this is associated with the 100 milliliters, so M1 is equal to 0.20 molar. So we're looking for M2. Okay, so let's go ahead and use the equation. If we're looking for M1 V1 is equal to M2 V2, divide both sides by V2. So M2 is equal to M1 V1 over V2. Now that we've figured out what was going on, let's go ahead and plug in our numbers. M1 is 0.20 molar sodium hydroxide. V1 was 100 milliliters. And then V2 is the sum of 100 and 150 of water added onto it. So that total now is 250 milliliters. Notice how my units for volume cancel out. So what I should end up with is concentration in molarity. This is 3 significant figures, but that's 2. So our answer will be in 2 significant figures. So it's 0.2 times 100 divided by 250, and we have 0.080. That's my 2 significant figures right there. Molar sodium hydroxide solution. Okay? All right, let's talk about some properties that are unique to solutions, colligative properties. So here, colligative properties only depend on the number of particles, not the nature. So if I had 1 molar sodium chloride, when it's dissolved in solution, I have sodium and chloride, so I have 2 molar of particles, okay? So the total number of particles will be 2 molar. Now what happens if I had 1 molar, let's say, potassium iodide? Well, it's the same thing. I will have twice as many particles, so the colligative properties will be the same, even though these are different substances. If I had 2 molar, let's say sucrose, or let's say glucose, let's say just glucose 1206, because when this dissolves, it stays together, it's not ionic, so it doesn't come into its particular ions, but I have twice as many. So this, believe it or not, will have the same colligative properties as 1 molar sodium chloride or 1 molar potassium iodide. It's the number of solute particles, okay, not the nature. So what are the colligative properties that we're going to talk about? Vapor pressure lowering, okay? The vapor pressure, remember, that's my pressure caused by when a liquid goes into equilibrium. And so it's going to have some in the gas state. But it turns out when I have a solution, that vapor pressure is lowered. Boiling point elevation. So if you look, the temperature of pure water boiling will be lower than the temperature of salt water boiling. There's an elevation on that. And likewise with freezing point depression, pure water freezes at 0 degrees Celsius, but salt water freezes at a lower temperature. So oftentimes if you look, our glaciers or icebergs actually that float on the ocean, while the ocean might be very cold, same temperature, but it's still liquid, but the pure water is ice that's floating on top because it freezes. There's a freezing point depression, and the salt water therefore freezes at a lower temperature. Okay, and then we'll talk about osmosis and osmotic pressure. Okay, vapor pressure lowering. So what happens? So basically when I lower it, as a result, of course, you'll see a shift here, and so my solution therefore at the same pressure will have a higher boiling point, or at the here we're talking about the freezing point. But let's talk a little bit about vapor pressure lowering. Why is that? Okay, so before we do that, let me just tell you the last concentration unit. That's molality. It's moles of solute per kilograms of solvent. We're not going to go into calculations in this course a lot. We'll spend more time in General Chemistry 1 with it. And basically, you're just going to do the same type of calculations with it. But we use molality when we talk about colligative properties. Okay, so when we do this, basically moles of starch in 0.5 kilograms of water. I want to make sure it's moles per kilogram of solvent. And then you get your 0.2 molality. And this is useful in terms of calculating how we get our freezing point depression and our boiling point elevation. And also, okay, but let's talk about vapor pressure lowering. So with vapor pressure lowering, now that you know how the calculations run, let's just talk about the concepts. When we have vapor pressure for a pure solvent, what happens is this is a sealed container, and this is in vacuum, and when we reach the temperature and this is in equilibrium, then this is my vapor pressure. But how much solvent can go into the gas phase is how much is accessible to the surface to get out of there. Okay, and it also depends on how strong these intermolecular attractive forces between your liquid is. When we put in a solute, and generally these are not volatile solutes, so they're not going to evaporate. So the red is my solute. There are two things that happen with this. One, you don't have as much solvent at the surface, so you have a lower probability of having a high kinetic energy one to escape. So that's why you have fewer that can go into the gas phase at this particular temperature. So remember, these are comparing the same temperature. The other aspect is depending upon the solute, if it's soluble, it's going to have the same characteristics as your solvent, right? And so that's going to also, you could have stronger attractions between your solvent-solute than between solvent-solvent. And that will also prevent your liquid from escaping into the gas phase. So basically the bottom line with this is that when I have a solution, I can't, at that same temperature, when we're comparing same temperatures, I do not have the ability to go into the gas phase as easily as if I were pure solvent. So that's why my vapor pressure is lower. Okay? So again, if I lower my vapor pressure, and remember normal boiling point is at 1 atmosphere, right? The boiling point. So this is when vapor pressure is equal to 1 atmosphere. Pure solid reaches it, but if I lowered it, then I had to increase the temperature more just to get more energetic liquid particles to escape into the gas. So I have to heat it more in order to get the vapor pressure equal to 1 atmosphere and therefore reaching my boiling point. So that's why we have a boiling point elevation. Now, where do you see this? Radiator fluid. Why do we add radiator fluid instead of pure water to our radiators? Because pure water, when it goes into our radiators, that means it's going to boil over at 100 degrees Celsius. Most cars, especially if you're going uphill like the Grapevine on the 5, are going to overheat. So oftentimes what we do, and we do this all the time actually, instead of just using water, we use a lot of radiator fluid. By using radiator fluid, now we've created a solution, and because we have created the solution, we get the elevated boiling point. So now our engines won't boil over at 100 degrees Celsius. It takes a lot more before our engines boil over. What about freezing point? Well, freezing point, remember, you have a liquid and they can slide past each other. So when it freezes, the liquid molecules have to line up into a nice geometric pattern, into a crystal to form the solid. What happens if you have solutes in here? It's a lot harder to basically organize yourself into a nice crystalline solid if you have something in between and you have to juggle around it. So by depressing my freezing point, by making it colder, then these liquid molecules are so low in energy, they just accept these irregularities and then they freeze. But you have to get it down to the point where they have such low energy, they're accepting it. That's why we get a freezing point depression, because at the normal freezing point for the pure liquid, it has enough energy, it can really move around the solute because it doesn't like having it there. It can't organize into a nice crystal. So those are two of the colligative properties, well, and the third being vapor pressure lowering, caused by making a solution. Osmosis, what happens here is that when you look at something like pure, this is my pure liquid, and this is my solution. It turns out my liquid molecules want to dilute out my solution, okay? It's kind of like if you had Hawaiian punch concentrate and you very carefully pour in the water, there is a gradient. I have high concentration of Hawaiian punch at the bottom of my flask, and at the very top it's almost pure water. But if you let it sit, what you'll see is that there's a migration until everything becomes even. When you put in a semi-permeable membrane, you prevent the solute particles from mixing evenly. So the only way you can try to make it so everything has the same concentration is by having my water permeate through the membrane and dilute this out. And that can be measured in terms of pressure. Okay, so in osmotic pressure, when that happens, it's the difference in pressure that stops the flow of water due to osmosis. Okay. When we talk about blood and osmosis, all right, why is this important? So isotonic means it's the same concentration of dissolved solute. This case is 0.9% saline. So there is no osmotic pressure because it's the same inside the cell and outside the cell. Hypertonic that means that there's a higher concentration of particles outside my cells than inside my cells. So what's going to happen when it's hypertonic and I have more particles outside than inside, then all the water inside my cells will try to get out of my cell to dissolve, or not to dissolve, but to reduce the concentration on the outside. Hypotonic means that outside my cell, the concentration of particles is lower than inside my cell. So is this important? Yeah, because of osmosis, now the water wants to go inside the cell to try to dilute out the concentration of particles inside my cell to make both outside and inside even. So iso in this term means that they're the same. Okay. So when we look at the effects, isotonic, that's why when we give IVs or we work with patients, we have to be careful. You don't give an IV of pure deionized water. You're going to kill the person, right? You need to make sure you have an isotonic solution so your cells in your body don't see any pressure, and it's the same. When it's hypertonic, okay, so what is this? So all of the water is escaping out of my cell to try to dilute out the particles, okay, outside of my cell, and that's why it's all shriveled up. Hypotonic looks like this. Why does it bloat out? Because all the water on the outside is trying to permeate into the cell to try to make it isotonic, to dilute out the particles inside my cell. And it'll keep going until the cell bursts. Okay, so just so you know, the end result, the cell is going to burst. And that's the effect. So that's why osmotic pressure is really important. And the reverse osmosis, we have to use basically work, usually in the either doing pressure or so. But reverse osmosis is doing the other way. You know this is automatically going to happen here. So reverse osmosis is forcing it the other way. And that's what we do when we try to purify water. So if you look at some of your bottled waters and it says it's purified by reverse osmosis, then just be aware you're going from a high concentration, you're making it a higher concentration. You're doing the reverse of what nature will automatically do. Okay, and that's